Um, Dr. Vasilis Bellos is an assistant professor at the Department of Environmental Engineering of Democritus University of Thrace in the position related with the integrated water resources management, the design and environmental management of hydraulic works. His main research interest is in the numerical modeling of water-related problems using mechanistic simulators of data-driven approaches. He has more than 10 years of experience in that field. He's participated in more than 10 research programs as a principal investigator or as a research team member, and he has written more than 20 articles published in the international peer-reviewed journals, while he has participated in numerous international conferences related to water science. He's also contributed in various hydraulic studies and technical reports. His expertise in hydrology, hydraulic engineering, and river hydraulics, computational hydraulics, hydroinformatics, and flood modelling, which he's developed. He's also developed the flow R2D algorithm for flood simulation in 2 dimensions, and he's a user of several commercial hydrodynamic and hydrological software. So without further ado, Vasilis, if you'd like to start sharing your screen, and then we can begin. Handing over to you.
Do you see my screen now?
Yeah, we do. And then in full screen. That's the one. Fantastic. Okay. All right.
Hey there. Hello. I wanted to thank you for my side for this invitation to participate in the conference and giving this lecture named Dam Break Modeling, Recent Advances and Future Challenges. Briefly, I am assistant professor in the Department of Environmental Engineering at the Democritus University of Thrace, which is located in Greece. As far as my background is concerned, I'm a civil engineer, focusing more in hydraulics and hydrology. So this lecture has the perspective of a hydraulic engineer regarding the dam break modeling, because this issue is an interdisciplinary field, as we are going to see in the next slides. So this is from my point of view, all of this topic. Okay, sorry. I thought it was something for me. Okay, so now let's go in general. We have 6 types of natural disasters: geophysical, meteorological, hydrological, climatological, biological, and extraterrestrial natural disasters. Our today lecture is focusing more on hydrological natural disaster, and this is a typical framework for risk analysis in order to perform a probabilistic design, which is the way we construct a hydraulic work. We collect historical recorded data, we perform a frequency analysis in this data, and we found the probability of exceedance over a threshold. It depends on the size we study. And then we define, in order to make this probabilistic design, we define a return period of an extreme event. Now, regarding the floods, we have 4 indicators, let's say, in order to see the impact. First of all, we have the number of events, the number of the people who are affected, the economical impact of the event, and one hard indicator is the number of the fatalities, the casualties after the extreme event. Here we can see for several natural disasters, we can see for 2017, the number of events. But this indicator is not probably is not very indicative of what happened, because it, even if the flood or the earthquake is small or large, it's counting +1. So an extra indicator is the number of the people who are affected, which again has some disadvantages, because probably these millions may be affected. The affection is rather small, but they are also counted. So another indicator is the impact regarding the money, let's say. So this is during the decades, the percentage of the GDP of flooding in all over the world. And finally, we can see the most hard indicator, the number of the dead people, let's say, which except of 1930, we have a very decreasing trend, I would say, for this indicator. So what is flooding? If we go to the terminology of the European Union and the European Directive, flood means the temporary covering by water of land which is not normally covered by water. This shall include floods from rivers, mountain torrents, Mediterranean ephemeral water courses, and floods from the sea in coastal areas. And this term may exclude floods from sewage systems. So what are the mechanisms which create the flood phenomenon? The first is the fluvial driver, which is the most common case. We have a river, and then after a storm, water depth is increasing and then exceeds the levees or the main channel and starts to enter in the floodplains, and then we have the flood. The second mechanism is pluvial flooding, which is the flood volume which cannot be captured by the sewer system in the urban environment. So all the water which is concentrated after the rainfall in the roads of the city creates a complex hydrographic network or defined by the topography of the city, and then we have the flood. The third one is the failure of a work such as the dam or the levee. The fourth one is the flooding in coastal zones, either by tides or tsunamis. And finally, we'll have the compound events, which means that we have in parallel a fluvial, pluvial, and coastal zone floods all together. So today we are going to focus just on dam or levee failure. So let's start on that. What are the mechanisms of dam break? First, we have the overtopping. We have a flood hydrograph enters in the reservoir, and this flood hydrograph cannot be propagated with safety through the spillway. Flood volume is overtopped via the dam body, and then we have the failure. The other big mechanism is the piping. Water is seeping through the dam body, fine sediments are eroded, and then we have the start of several circular holes which are opened, and then water finds the way to erode the rest of the dam, and then we have the final failure. Here we can see some phases of the overtopping. It is like that, with some pictures from a real event. And here we have some phases of the piping. A very interesting, and we were lucky, I would say, to capture these photos during a real dam collapse in the USA. The name of the dam is Teton Dam, and the failure was occurred in 1976. So in the left, we can see the first time moments that the hole is created, and the guard, the security which was there, started to have some photos every 5 or 6 minutes or something like that. And here we can see the evolution of the phenomenon till the total collapse, let's say. Let's go, first of all, let's go to see some historical dam collapses and see some of the main causes. We can see that we can have spillway design error, geological instabilities, landslides, poor maintenance during the years, extreme inflow after a storm, human errors, piping, especially in earthen dams, earthquakes, etc., etc. Briefly, we have over 100 recorded cases. The older case is in Yemen in 575. The impact was 50,000 people forced to immigrate. And we have two big records regarding the casualties. Both of them are in China. The first is Banqiao and Simandan dams, which were collapsed in 1975, and the result was 170,000 casualties. And their second record is the sabotage in the Yellow River and the failure of the levees, which were controlling the river in 1938 during the Second Sino-Japanese War, where casualties were in the recorded to be more or less 500,000. This is mistake, is more than 700,000 fatalities in total, and about 7,000 of these fatalities are in Europe. The majority of the events are in the USA, and as we study the historical records, we can see that over than 30%, over the 30% of the total events is recorded in the States. Here also we can see some historical failures. The year of the construction, the year which is failed, the mechanism, and some characteristics which is the shape of the bridge, which is the geometrical characteristics of the bridge, etc., etc. Some very interesting failures. It's as recorded in Europe. We can see the famous Malpasset Dam, which was collapsed in 1959. To the left, we can see a picture before the failure, and at the right, we can see the picture after a lot of years. The area is abandoned there, and some people have captured some photos in order to show the case study. One more very interesting failure, which is not a dam collapse, it's the Vajont Dam in Italy in 1963. Vajont Dam is an arch dam, and there was a landslide. Half of the mountain entered in the reservoir. A huge wave was created, which was overtopped the arch dam, destroyed a city in the downstream area, and the dam body is not damaged at all. It still works, it still is there, but it doesn't work. It is without water. Here we can see in the right a 2D picture, just the dam without water in the upstream. Here we can see, and here we can see a simulation of this phenomenon. We can see the landslides and the creation of the flood wave, let's say. Now, what type of dams do we have? We have the earth dams, which is constructed with earth, rocks, and materials coming from the nature. We have the gravity dams, which is made by concrete. We have the arch dam, which are made also by concrete, but they have a different arch structure. And we have the roller compact concrete dams, which is a hybrid form between earth and concrete and gravity dams, let's say. Now, what failure do we have depending on the type of the dam? In the earth dam, we can say that the failure time is rather slow in comparing with the other types. In the gravity dams, the failure is much more faster than the failure occurring in the earth dam. And in the arch dams, due to its structure, the failure is abrupt. Finally, in the RCC dams, due to its hybrid form, we don't know a lot of the failure mechanism, but we assume that the failure is something in between the failure of an earth and the gravity dam. Here we can see a small earth dam failure.
There it goes. There it goes.
And here we can see a small gravity dam, how fails. You can see that the mechanism is the mechanism of the failure is much more faster, let's say. Now, the major issue for the engineers is trying to simulate all of this phenomenon in order to prevent the bad consequences, let's say. What is numerical modeling? It's a box of mathematical transformation from a simple explicit equation to a system of partial differential equations in order to simulate a natural phenomenon and create algorithms. And in our era, the several software exist with which we can simulate and then predict and then design the corresponding work. This is the main structure. This is the main structure of a model. We have the input. We have a structure of the model, which is several parameters correlated one each other with several mathematical transformations, and then we have the output. So the first approach coming from the 19th century in order to simulate all the flood wave created after a dam failure is the Ritter solutions. We assume a 1D flow, and then we assume a water depth, which is a water volume which is still, and then we assume that suddenly the dam just collapsed, and then we can calculate all of these profiles of the water depth in several time moments, and also we can calculate the flow discharge in every position. This solution is rather naive in our days, and we cannot use it in order to design a real hydraulic work. But this is the history and the first approach to trying to simulate all of that. In our era, we use the framework which is called integrated modeling. In integrated modeling, we couple several models in order to find in order to derive the final results. So in a typical case study, we have first we have the input, which usually is the meteorology, meaning the storm, the design storm with which we design the dam. And then we couple first a rainfall runoff model, which transform this rainfall to the runoff to the reservoir of the dam. Then we have, using this inflow, we have the dam breach, the dam break model, and then we derive with that the flood hydrograph created after the dam failure. And this flood hydrograph is propagated through a hydrodynamic model, which can be either 1D, if we have a river reach, or 2D, or we can use 1D in the first upstream part, and then since this flood wave hits a city which is located in the downstream area, then we can take the output of the 1D flood model and use the 2D flood model in order to simulate all the potential flood impact. We do all of that framework to several reasons, and which is one of the main reasons is the computational cost. We cannot calculate all of that using a 2D hydrodynamic model because the area is huge and no model can be used in order to simulate this computational burden, even using a high performance computing facility. Hopefully nowadays we have several software packages that we can use it, all this integrated framework, and this is very helpful, especially for practitioners engineers who work in the technical companies. Some stuff about the modeling. Rainfall runoff models simulate all the processes related with the water cycle. The basic unit, the scale is the catchment and the characteristics of the catchment. They are conceptual and empirical models, and they are their scale is much more coarser than the fluvial scale, which is the hydrodynamic scale. For flooding, the emphasis is given in the surface runoff. And here we have some types of models like rational method, unit hydrograph, etc. Now, for the dam breach models, the most easy approach, but not correct, is to assume that the failure is abrupt and total. So we don't need model, just a proper boundary condition of the hydrodynamic model. In reality, we have a partial failure in a considerable time interval, and we have several types of the breach shape: trapezoidal, orthogonal, triangular, and parabolic. Of course, all of that shapes are an abstract from reality. We assume that the breach shape is like that. It's not, of course, the real breach shape, which is chaotic. How do we estimate the dam breach parameters? The dam breach parameters is first the geometrical characteristics of the breach, the failure time, the time interval requires that the collapse is finished, the discharge coefficient, which is a coefficient that defines the outflow, and how do we estimate all of that? This is a very hard question, which is an open challenge. We usually have some empirical equations. Probably there is a guru which assumes that the parameters is like that. And the most easy and convenient case is that we have some handbooks, and then we take these values from the corresponding bibliography in order to be not correct, but in order to be in accordance with the legislation of the country. Here we can see some of the parameters which defines the geometry of the dam bridge model. And of course is and as we can see later, the required time for the completion of the bridge, which is not a geometrical characteristic, but it's crucial for the dam bridge model. Since we skip this model, we have the hydrodynamic modeling. So hydrodynamic modeling is based on integrated form of the Navier-Stokes equations, which solve the flow either in 2 dimensions or in 1 dimension. This set of equations is named as shallow water equations or Saint-Venant equations in 1 or 2 dimensions. These are physically based models. We have 1 continuity equations and 1 or 2 momentum equations, depending on using the 2 or 1 dimensional form. Here we can see an effort of 1D simulation. It is for a benchmark a benchmark physical model. And here we can see a 2D simulation, again for a benchmark physical model. Now, the most interesting thing for today's lecture is how we can couple the dam bridge model with the hydrodynamic model, which is used for the propagation of the flood wave. The input for the dam bridge model is the characteristics of the bridge shape and the discharge coefficient. The structure of the dam bridge model is the Weir equation, which is very typical in hydraulic engineering, and the output is the flat hydrograph created in the location on the dam. Now, this output is the input for the hydrodynamic model. So, using that input plus the parameters required for the hydrodynamic model, and using a structure either 1D or 2D, we can have the output of the model, which is the flat hydrograph in the downstream area, the water depths, the inundation boundaries, etc. Since we gave the general framework of the simulation, now we can go to what are the uncertainties to all of that. We performed an uncertainty analysis for a real-world case study, a dam which is under construction now and is created, and the type of the dam is an RCC dam. The case study is located in Crete, Greece, and we performed a Monte Carlo analysis, assuming a plausible range of all the parameters required from the dam bridge model, using some bibliographic values. Since the bibliographic values, the handbooks for several type of dams give several ranges, we used this envelope of ranges and in a plausible way. So we can see here the range of all the parameters. Before we go to the Monte Carlo analysis, we performed a sensitivity analysis in order to see what is the influence of every parameter in the result. In order to perform this sensitivity analysis, we use the well-known Morris method, and then which calculates the elementary effects. As big is the mean of the elementary effects means that the parameter affects a lot. And as big is the standard deviation of these elementary effects means that the affection in the final result is nonlinear. So here is the results of the sensitivity analysis for the flood peak in the location of the dam. And we can see that the time and the width of the breach is the most crucial parameter, let's say. So we took all of that, and then, except of the location of the dam, we tried to see how it goes, all of that, in the space. And we can see that time starts to be the most crucial, but in the end, it's not so much big. Here, in the 15,000 meters means that if the dam location is in the zero, the 15,000 meters is in the sea, 15 kilometers away the dam. It is how the flood peak is propagated during the river reach. And here we have the same, but not for the flood peak, but for the maximum flood depths which are simulated in every position. Since we finished the sensitivity analysis, we'll go in the Monte Carlo, and we can see that assuming that the parameters are drawn from a uniform distribution, here we can see the flood hydrograph created in the location of the dam. The range is very big. It's over than 10,000 cubic meters per second, the flood peak. And if we try to find the statistical character, to fit a distribution and find the statistical characteristics, we see that for the flow peak, normal distribution works well, and we can fit that distribution in the data. But as we go downstream, and we can see, we try to do the same, fitting a distribution for the same data for the flood peak, we saw that this normal distribution doesn't work. The data has a skewness. So we used a distribution such as Weibull distribution, and then we tried to fit it with reasonable good results. So this is the fitting with the flood peak, for the flood peak, and this is the fitting for the maximum flood depths in several positions. 15 kilometers away from the dam, 10 kilometers away from the dam, and 5 kilometers away from the dam. Now, an interesting part is that if we calculate using the parameters of the Weibull distribution, the coefficient of variation, we can see we have the left graph. And we can see, if we assume that this coefficient of variation, that it's a metric for uncertainty, we can see that uncertainty is much more crucial and important in the beginning of the event, in the position of the dam, in the zero, and as we go, as the flood wave is propagated until the sea, uncertainty is decreased. And one other interesting finding is that if we divide the coefficient of variation to the water depth, we can find a constant, let's say, ratio, which is more or less about 2.5. This means that the flow peak is characterized by much more and 2.5 times more uncertainty than the water depth, which is expected since the flow peak, the discharge or the velocity are calculated with the momentum equations, which is more nonlinear than the continuity equation with which we used in order to calculate the water depth. Now, let's go to another big issue from a hydraulic engineering perspective, is the calibration of the parameters required in the hydrodynamic modeling. In general, we say that parameters of the flood simulators should be calibrated, especially in hydrological scale, because its uncertainty is much more important, much more bigger. But the problem is that we don't have data. The majority of the basins are ungauged, and if they are gauged, flood usually destroys all the monitoring system because it's a violent phenomenon and not it's beyond the normality, let's say. So what are we doing in order to cope with all of this problem? First, we try to find some proxy data, or we create synthetic data sets using some physically based laws derived from smaller scales. Here I will focus more on the proxy data, which is a quite important topic. We can find proxy data from several sources. Physical modeling is the most old but most expensive way to derive some data. Post-event forensic research, crowdsourced data, insurance companies, emergency calls from the services, and remote sensing. Let's go from the convenient approach. I suppose we all know Hurricane Katrina, which hit the States in 2005. So there were research teams who tried to make a physical model and simulate the flood after the breach of 17th Canal Street in New Orleans. Here we can see some indicative pictures of the physical model. Another way to collect data in order to calibrate the hydrodynamic model is the forensic research. Here we have another historical dam collapse, is the Tow Dam break in Spain in 1982. Here is a picture after the dam failure. And then we have an effort to reconstruct all of that. To the left, we have a reconstruction of the inflow hydrograph to the reservoir, and to the right, the outflow hydrograph after the dam collapse. Forensic research is also performed by this research team, which using interviews in the field, managed to collect the maximum flood depths in 21 points across the inundated city, which is the name of the city's name is Sumacarcel. And here we can see, using the interviews, the 21 points floods. Potentially, still not, in my knowledge, it's still not used, but potentially it's not used for a dam break flood. It's used for another type of floods. Crowdsourcing using the social media is a good source in order to collect proxy data in order to calibrate the hydrodynamic model. Insurance companies, the calls for the emergency calls to the 911 or whatever the number is in every country, and remote sensing. After a flood, the aftermath is still water in the flooded area, which is probably captured by a satellite, and then we can have several algorithms in order to identify which are the flood boundaries. Now, finishing the two-day lecture as a takeaway message. First, there is a problem for performing a dam break analysis, how to calculate the risk. If the driver, as we saw that if the drivers of failure are, let's say, predictable, such as the meteorology, which means a storm, or a geophysical driver, which is the earthquake, are predictable, we have so many other drivers, such as a technical problem or a war sabotage, which these situations are not predictable. If we take all of this context, coupled with that there are no lot of data, because we do not have lot of recorded cases, the problem comes now that we cannot derive a return period in order to design over a flood created by a dam break. Another challenge is what is going in the mechanism. We know that the phenomenon is chaotic and not the flood created and the propagation of the flood, the collapse as it is. So there are a lot of open research questions and an open interdisciplinary field which can collect scientists from all the backgrounds: geotechnical engineers, hydraulic engineers, geologists, hydrogeologists, solid mechanics. Even the army can help us with giving some practical advice with the explosions. Finally, what is going with uncertainty? We saw that uncertainties are very significant, especially in the area near the dam, as far as the flood wave is concerned. Can we estimate with a rational way the flood impact at the downstream area, for example, in order to perform a proper flood warning system? Because according to my view, till now, we just calculate a big number, a big flood peak, and then we say, okay, let's try to be safe from that big number. But we are not sure at all what is going to happen. So this is from me. I wanted to thank you. And I'm open for questions or a discussion.
Fantastic. Thank you so much, Vasilis. Really insightful presentation, and thanks for sharing your knowledge with us today. So I'd like to open the floor for any questions. I'll get the ball rolling with one. I guess the first thing that came to mind for me, because I also was working in an industry with a lot of lack of data, and I initially started using Monte Carlo, but I found that I was making for myself too many assumptions around some of the distributions, because there just wasn't the data to be able to inform those. And I'm wondering whether you considered any other techniques that would have been able to help you estimate the more chaotic or unpredictable phenomena, like, technical difficulties or the sabotage, like you say. Like, I was using imprecise data techniques, but I'm wondering whether Monte Carlo was the only technique that you considered for uncertainty propagation, or did you consider other techniques in your analysis?
For now, just Monte Carlo. Yes, but I'm open for that. I'm very interested in. I'm not a data scientist. I work with statistical analysis, but okay, my background is hydraulic engineering, so I would be very glad if we to find an interdisciplinary context to couple all of that. Yeah.
All right, yeah, fantastic. Well, hopefully, I think we're running a little bit before schedule, but when Andreas talks later about the HUMA project, hopefully there'll be some kind of scope for, yeah, bringing some data analysis or risk analysis into your research, perhaps. Have we got any other questions from the audience at all? So another question that I would have is whether, hold on, I've written it down here. Yeah, so you mentioned some of the other research areas that you think it kind of stimulates, your project needs to stimulate further interdisciplinary nature. I'm just wondering, how does dam break modeling research that's already being conducted, how does that already relate to some of the fields like civil engineering, hydrology, environmental studies? Are there many kind of projects or kind of university departments that make that connection?
No. It's due to its difficulty is a very limited area. In Greece, for example, we have from our legislation for a new dam, the state advises that a dam break analysis should be made, but it's an advice. Now they have started to do this kind of analysis, but I think that the majority of the practitioners, they just use some commercial software. They put the button and they just take a big number, a big flat peak, and they try to say that this is the flat peak and maybe we can have some measures and so on. From water science, let's say, perspective, this is the thing. I don't know from other fields what's going on very well, but in my knowledge, I think that the area is very limited. There are very few things. We know very few things about that.
Okay, fantastic. And when you were saying that when the analysts do this kind of dam break analysis on their project, and it's quite rudimentary because they're not spending too much time or effort on it, I'm wondering, based on the historical record and the fact that this is kind of a relatively new domain, how many dams has this sort of analysis actually prevented them from collapsing? Like, do we know by what percentage it increases the likelihood of you not having a dam break at all?
In Greece, there is no dam collapse.
Yeah, okay.
So this is the problem, that there are very few. We are lucky that there are very few.
Sure.
But it comes with a problem.
Yeah. Andreas has a question. Sorry, would you like to unmute yourself?
Well, more or less, precisely to make the point of Vasilis. Usually, when you have to do a dam failure analysis, is because something is really wrong with maintenance or with how you administrate or control these assets. Usually, water dams have huge inbuilt safety factors. They are usually done in a conservative manner, but you have mess-ups. I don't know, Vasilis, if you have heard about the Hydroituango Dam here in Colombia.
No.
Well, more or less, maybe it's worth even to make a small presentation about that, although the information is quite sparse. It's a large dam. More or less, you have a 100-meter gravity wall they did a lot of things wrong during analysis. So, for example, do you have a discharge tunnel? They blocked that. They tried to build another discharge tunnel, more or less like 70 feet up from the previous one. That tunnel collapsed because the most accept theory is that they think did the digging of that tunnel wrongly, and then we had to face the serious problem that the dam began filling without a discharge tunnel. So more or less they have to build half of the dam in a month, and with quite sui generis weird stuff. So this is also to stress the point that yes, dam breakages analyses are quite strange, but are quite critical when you depart from strong guidelines. And I say that is quite common in the global south.
Yeah, it's true. I think now I remembered this dam. It's a few years ago, correct?
Yes. Of course, they claim now that everything is safe, but we don't know.
Yeah. The thing is that even there is a big safety factor. For example, in Greece, the design storm is the return period is 10,000 years. It's a huge storm, which is it's not it's out of the mind. But the problem is, in order to design this storm, we have records of 100 year, which is the best case of rainfall, and we have 100 year of rainfall. We have maximum daily maximum or something like that. With a more dense time step, we usually have 20 or 30 or 40 years or something like that. So you fit a distribution there like a gamble or a generalized extreme value and so on, but you take a probability of so small, and no one knows what is going in the tail of the distribution. The first one is that. The second one is that even in that point that that something is, let's say, predictable, as you can see in the beginning, when we saw some data, and we saw the hard indicator, which is the people of the casualties. Here we can see that everything is destroys all the analysis, because the majority of the casualties is in 30s due to a dam levee collapse, which is not created from a problem of maintenance or an earthquake or a big storm or something which can be probably predicted or probably can be prevented using very good safety factors. This was a sabotage, a war sabotage. No one can goes on that. So you can see that the majority of the casualties come from a fact like that.
Well, more or less being a little bit of a devil's advocate, have you explored the topic of natural dams? For example, when you have a landslide, it blocks the river, and then you make this lake.
Which creates, if it collapses, creates flash floods. It's in a smaller scale, so it didn't go in that analysis. This analysis is just for from human-made constructions. So no,
but I am talking in general. If you have are exploring that.
No. It's actually a very difficult thing as well, because it's very difficult to predict how it happens.
No, maybe I'm going to present a case I was involved in while I was in China. Precisely, it's quite interesting. We have more or less this happened in Tibet. We have a landslide. Firstly, it blocked the river. The river eroded the blockage naturally. Then a second landslide happened, and that provided a nice opportunity to assess this issue in detail.
I see, yes.
All right, thank you, Andreas, for that question. Do we have any other questions from the audience? And if not, I'd like to thank our speaker again. Thank you so much, Vasilis. Really great talk. And then I'll hand over to you, Andreas, if you'd like to do your 5-minute presentation from humor.
Thank you. Don't worry. More or less, this is a little bit of advertisement from our co-host. I am right now collaborating with them, and the idea is to explore ways to collaborate in the future. So let me talk briefly about them. It's just what we can call a 5 minutes, 5 slides presentation, and we'll appreciate to have your feedback and see what we can explore together. So what is Antofagasta? Oh, so more or less Antofagasta is a major, sorry for the animations, I made a mistake about that.
Andreas, we can't see your screen. Actually.
Oh, perfect. Oh, sorry about that. Waiting a moment. Sorry about that. Wait a moment. Okay, are you still blocked?
I am. I'm not sure about everyone else, but I can't see your. There we go. I think something's showing now.
I guess
yeah, I can see it.
So more or less, this is a really short assessment. So, what is Antofagasta? So, well, sorry for the animations. Sorry about that. I will delete this stuff so I can put you in a regional context. So, Antofagasta is a region in northern Chile. If we zoom, is next to the Atacama Desert, which is one of the most arid regions in the world. In the tail, if we zoom out, we go into this section of northern Chile, which is quite diverse. What you see over there is called the Salar de Uyuni, which is the largest, among the largest salt lakes in the world, and is quite famous because it is estimated that 60% of easily reachable lithium is in there. As you can see, the area is quite huge. The Geuma consortium is based in the city called Antofagasta, which is by the sea and provides access to northern Chile. The Atacama is the most arid region, is the aridest, most arid region in the world, as you can see. However, some weird things happen when they get seasonal rains. We are talking about that the region gets 70 millimeters of rainfall per year, and usually this comes together in a single season. And when you pour water on a desert, things like that happen. This is called the Desierto Florido, more or less the flowering desert, and dormant vegetation just take up. And more or less, the main industry in the region was saltpeter. And more or less, this thing was the original meaning fertilizer. When synthetic nitrogen fertilizer fabrication was made by Faber, the industry became obsolete. But fortunately, they uncovered copper deposits. Now, Chile is more or less the largest producer with more or less 20% of the world tally. And we have several million tons capacity in the region, being amongst the larger mines, the Chuquicamata mine, which makes more or less 350,000 tons per year. See? The question is, why Antofagasta? It's because it's a region that is quite well suited for the energy transition. There is vast sunshine, as I told you, is quite arid. We have sizable, easily reachable underground lithium deposits through in diluted salts in water. So the water is pumped and then it's led to evaporate, and that's the reason we have these pools. And also it has some relevant wind measurements. Darker, you go into more mean wind velocity. Antofagasta is right there, so we can get more or less on average winds up to 8 meters per second, which is quite good to be on shore. And in the region, through the mountain valleys, we have places when you can have larger options. But of course, the largest opportunity is in Argentina. So definitely it's an interesting region because it's well poised for this new paradigm regarding energy generation. But of course, we have also critical challenges. More or less, this is the most relevant ones. Being such an arid region, we face a basic water deficit. So precisely there have been extensive projects by mining companies to produce dry tailings and really try to recover as much as possible water from mine waste. Also, there are plans for a massive desalination. Currently, Antofagasta gets roughly 1/4 of its fresh water supply from ocean desalination. But of course, local contamination with mining byproducts is quite a concern. The other problem is that sometimes rainfall is quite scarce, but due to climate change and really changes on the atmosphere, we have experienced flash flooding, and really catastrophic one. Told you the rainfall is 70 millimeters per year, and we can get events that produce 700 millimeters in one day. So of course the region is, the geomorphology is not well suited to deal with this, and we end with catastrophic flash flooding. And precisely we face also the problems that the Vasilis told about, trying to identify what is the extreme event. Of course, even extreme value distributions go short, because definitely is a completely different phenomena. And in top of that, we are in Chile, which is the most active seismical region in the world. More or less 60% of the total moment release that has been observed in the past 100 years occurred there. More or less, you have in the region a magnitude 8 earthquake each 20 years, plenty of magnitude 7, magnitude 6 occurs almost 1 per week. And despite the really strong adaptation of Chilean building codes, still you observe large damage. And if you couple that with what happens on industrial facilities, you can expect a lot of downtime on critical industries. So going back into what is GEUMA, is a consortium of the 2 largest universities in the region, with focus on their engineering departments. Firstly, they arise to improve the student experience, and then they are trying to leverage their contacts with the local mining industry, with the local governments, to develop new products and really cash in on the new economic reality that is going to grow forward by net zero. And now they really want to engage with international institutions like the Institute of Risk and Uncertainty and the University of Liverpool, and industries to really develop more or less a really interesting cluster with worldwide impact in the region, adapt to the needs of arid regions worldwide. Thank you.
Thank you very much, Andreas, for your great short little presentation. Do you have any questions for Andreas? And if not, then I will make some closing comments before kind of asking for an open discussion, which will stop the recording in a moment. So without further ado, just bear with me a moment. I just want to thank all the attendees and the speakers for their valuable insights and contributions during the conference. The discussions have been thought-provoking and gained a deep understanding of how different approaches can be used to improve safety and support sustainable and responsible extraction in mining and the energy industry. I hope that this conference day will serve as a platform for networking and for future collaboration, and hope to see you at our hybrid event on the 9th and 10th of February. So thank you very much, and I'll stop the recording.